that gives rise to a Zutta potential, which is harmonic in the transverse direction. So that is the transverse confinement, and the chain is along this direction, the confinement of which is given just by a DC quadrupole. So these blades are segmented, so I can put like high potentials on the ends to confine them in this axial direction. All right, so that's the trap.
The trap itself is made of what?
The substrate is silica, and then it's coated with titanium and gold. And then it's hand assembled on this holder. So it's not perfect.
The electrodes themselves are their pattern. It's like PCB. Like I don't think of them as a circuit board kind of thing.
Well, I mean they're like, so the alumina is cut. So it's not like a surface. So it's like a block of alumina that is just cut using mechanically cut, basically. Alumina. You could use sapphire also, yes.
And the white thing is Teflon.
This white thing is Makor. Yeah, because it has like good thermal conductivity. So these blades heat up after some time because it has like 100 volts of RF on it. And then, yeah. All right. Okay. So moving on, the native operations that we have in our system is the single qubit gates. So here I'm showing you just the Rabi flopping. All right. So I have 5 ions, and I'm just like Rabi flopping each one of them. The unitary operator looks like that. So this is a pictorial representation of the beat node that each ion sees. All right. Because I have these 2 frequencies, and you get this beat node at hyperfine frequency that does this Rabi flopping. So by shifting the phase offset of the beat node, I can choose which axis on the block sphere I'm going to rotate the qubit. So that decides the phi, and the duration of the pulse decides the rotation angle theta. Right. So you have full control over Rabi flops. This is pretty normal. The 2 qubit gate is a little more tricky. So let me go into a little more detail about it. So here what I'm showing are the different transitions. So let's say I have 2 ions, and I want to do a 2 qubit gate on it. So this would be something that entangles the spins of those ions. The way you do it is, so you have the carrier transition, and for 2 ions, you have the 2 normal modes of motion, right? So in frequency space, these are the different transitions. So let's say I take my Raman beat node, and I actually put 2 beat nodes on the ion. One is red detuned, one is blue detuned, and they are closely detuned to these normal modes of motion. All right. So the evolution that you get then is a spin-dependent displacement of each ion. So you could think that the internal spin of the ion is entangled with its motion. So depending on the spin of the ion, it gets displaced. So what it looks like in the phase space trajectory picture is that each ion, if it was a single wave packet, it splits into 0 and 1 in the x basis, and then it follows this trajectory. Now, if I choose my detuning correctly of these bichromatic beat nodes, these are symmetric about the carrier. So this detuning is delta from each one of the mode. And if I wait exactly 1 over delta time, then I end up closing both the phase spaces. So you have to think of it this way, that you have the spin that is getting entangled with the motion, but there are 2 modes of motion here. So the spin gets entangled with the common mode of motion, and then it also gets entangled with the tilt mode of motion. And if I waited for a long enough time for a judiciously chosen detuning, then I can cancel out. So sorry, I can cancel out this first term because it closes in the phase space. So my spin gets decoupled from the motion. This is a Momer-Sorensen scheme of doing this spin-spin interaction. So the first term goes to 0 here, and what you're left with is a second term. This is a scalar. This is a spin-spin interaction term, and that is your entangling operation. All right.
So I think this looks a little more complicated than if you have a common degree of freedom, like motional degree of freedom. Why can't you do it? I mean, it's probably got to do with the details of the system, but like
Yeah.
But here it looks like it's not.
It not.
Simple picture.
It's not that simple because so what you're talking about is the Sirac-Zollner scheme, where what you do is you encode the spin state into the motion, which is shared by the entire chain because it's a normal mode, and then you do a reverse pulse on some other ion, and that is how they communicate. So this is not happening in those yeah. So yeah, so this one is more continuous. And the way, one intuition of this is that, let's say the sigma x wave packet, like sigma x up wave packet of both the ions moved in the same direction. The sigma x minus wave packets moved in the other direction. So the distance between them did not change. But the sigma x up and the sigma x down component of these two ions moved in the opposite direction. The distance changed, so that gives you a relative phase, because now the energy is different. So you get a spin-dependent phase, and that in some basis is an entangling operation. So that is one way of looking at it also. It's a control phase or control knot, yeah, yeah. All right. So if you have 5, then you have five ions, you have 5 modes. And the picture is not so simple. It's not like 2 trajectories closing, but there are 5 trajectories that needs to be closed. And the detunings being incommensurate, hence there is no like correct time to wait so that all of these different modes close at the same time. So what you end up doing is this pulse shaping scheme where you modulate this spin-dependent force. So you just like modulate the laser intensity, and then these trajectories take up this funny shape. But the good thing is that at the end of the gate, all of them close. So you end up disentangling the spin with all the modes of motion, and what you end up having is then just this spin-spin interaction term, the control phase gate.
Shaping is just on the amplitude.
On the amplitude, yeah, only just there. But you could also do it in phase. People have been doing it in phase. Yeah.
Shaping will be different from the different pairs of modes?
Yes. All right.
Do you have a way to determine that from the
Nu-
parameters you gave?
We first determine it numerically, then we determine it experimentally. So numerically, we determine what the shape is going to be. That's why this is normalized omega. Experimentally, we scale this thing up and down to hit the correct accumulated phase, 2-qubit phase. Yeah. So
What's the feedback in the experiment? Just seeing whether the
we are yeah.
the correct state you have prepared, and then you
Yeah.
correct your gates.
So this is what we exactly do. We start with 0, 0. We do the entangling operation. We end up getting 0, 0 plus 1, 1. When the phase is exactly pi over 4, the populations are 50-50. And that's the correct intensity. Yeah. All right. In the experiment, how would you implement this? Let's put the pulse shaping on the global beam, and let's select the qubits that are going to get entangled using these individual addressing beams. All right. So if I have 2 beams lighting up these 2 guys, then they are going to have an XX gate, or the spin-spin interaction. All right. This is the unitary evolution. By changing the laser intensity, we can control these 2-qubit phase chi. So that is sort of important in certain gates. More importantly, the system is fully connected. So I can choose any 2 pairs. They're almost uniformly and fully connected. So having this connectivity, it reduces the overhead of doing 2-qubit gates in general, or in general algorithms. All right. Now, if I wanted to write down my algorithm in the textbook language, which would comprise of Hadamard's, Z rotations, and control knots, control phase gates, then I would have to form a compiled gate, which would have elementary gates executed in a certain order in order to get this control knot conventional operation. And the same goes for the control phase gate. So this is just the decomposition of that. And I could look at my control knot and control phase gate fidelities here, doing a partial tomography of the system, is that if I start with 0, 0, then it should not change. But if my first qubit is 1, then it should flip it. and this is happening with an average 98% fidelity. The controlled phase gate happens between the 2 qubits. If my second qubit is in the state 1, then I'll get a phase kickback on my first qubit that was prepared in the 0+1 state. Then I can do a rotation and measure it, so I will see this phase reflected as I do this controlled phase gate. Whereas here it doesn't change anything. Anyway, so now that I know that these modular gates work, I will go ahead and do an algorithm. The way I will then program my entire setup is that I'll choose an algorithm which will have a circuit. Each elements of this circuit are going to be replaced by these composite gates, so I call that a quantum compiler. It's basically a decomposition that has been like hard coded inside a computer. I have already done my optimizations to make sure that these single and 2 qubit native gates are implemented with the proper pulse shapes. So that is pulse shaping. And in the end, I'm going to execute that on the hardware, right? All right. Okay, so going over a few examples here. So the first one is quantum Fourier transform. What we did in our setup is initialize everything to 0, then we do a state preparation to start with a superposition. Now you could put some modulations in these coefficients and then do modulations in phase, amplitude, etc. on these coefficients, and then do a quantum Fourier transform and see if the outcome is what you expect to see. So the first example.
Just a question. So you have to measure all the nodes simultaneously, right? There is no selectivity. So if I say I have to measure the first and third, I can't do that.
No.
You have to measure all of them together.
Yep.
Right?
Yep.
So you say that you have to measure all qubits at the same time?
Yes.
Say that I'll measure qubit 1 and leave the other.
Not yet. Not yet. Yeah.
Okay. That's usually not important if you're running algorithms, because you have to measure all the states. Yeah, but for the algorithm, any code. Yeah, sure.
Okay. So my first example, let's say the input state is a superposition of this. I write it down in base 10. So this is showing a periodicity of 8. So 7, 15, 23, 31. You do a quantum Fourier transform. What you end up seeing, so this is a 5-bit quantum Fourier transform. So you end up seeing 8 peaks here, reflecting the periodicity of the input state. The squared statistical overlap sort of gives you the practical fidelity of the system. So the squared statistical overlap is just taking the product of the theoretical probabilities with the experimentally obtained probabilities and then squaring it.
Assuming the equivalence or
No. This is like the final outcome of the algorithm, and I just have my probabilities. So I just have, yeah. So I just have the diagonal density matrix elements. Yeah.
I think he's asking is that are the theory numbers including are they the ideal numbers, or do they include the anticipated equivalence in your
Oh, I see. Oh, they're ideal numbers. Yeah. All right. Then I can go ahead and do it for various other periodicities. Anyways, it works. Then I want to find out a phase modulation in my input state. So this is a quantum phase estimation protocol. What I do here is if I have an equal superposition of all the input states with a linear phase modulation, and I do a quantum Fourier transform on it, then my outcome is directly proportional to the phase modulation that I had on my input. So here what we have done is we have scanned the phase in steps of 2 pi over 2 to the power 5 or 2 to the power 6. So for all those phases that can be resolved using a 5-bit, you get a single peak. For all those which are like halfway between the next one and the previous one, you get like peaks in 2 adjacent populations. Anyways, so you can basically resolve this phase up to 5 bits with a fidelity of 60%.
So the way I should look at this plot is that your particular phase is encoded as given on the x-axis.
Yeah.
The final result of the output will give you a peak at that output.
Yeah. Yeah.
The height is telling you how good it is.
Yeah. So if I run it 10 times, then 6 times I'll get this peak, and I will know that this is 23 over 32 times 2 pi phase. So moving on, So, all right, so these were like a couple of algorithms that we covered. Then we did some experiments where we wanted to do some quantum error detection. So quantum error detection and subsequent correction becomes important for bigger quantum systems. So you can have a system that where the decoherence grows with the system size, obviously. But if you had a way to non-destructively measure the system by looking at, let's say, its parity, or if it has a phase flip, etc., and you could find out which exact physical qubits in the system had an error in it, then you could go back and correct it, and hence preserve or eliminate the error in your system. And that's basically the idea behind quantum error correction. It removes the assumption of perfect encoding and perfect operations in your system. So it's kind of important. And people have tried to show preliminary error detection and error correction protocols. So we also did one of those. And I'm going to sort of give you a brief introduction of what it's all about and then tell you what we did. So let's say that you have a logical qubit. That's a logical qubit. L stands for logical. It can be in a superposition, sure. But I want to encode it in 3 physical qubits. So this in the lab is going to actually be this. All right, so it will be 0, 0, 0 plus 1, 1, 1. So 3 qubits representing one logical bit of qubit of information. And this is a very simplistic circuit where you have a couple of ancilla, and what you are trying to measure here is sort of bit flip errors. So if your ancilla initially were initialized.